Good afternoon to everyone. Next topic in PDC subject, next topic is low pass filter, which is acting as an integrator. So what is the use of integrator? Integrator which is used in the summation purpose. Okay. So low pass filter means low pass filter. What is the definition of low pass filter? Low pass filter only allows the low frequency signals, and it attenuates the high frequency signals. So that is known as the low pass filter. Low pass filter means the filter which allows only low frequency signals and it attenuates the high frequency signals. That is known as a low pass filter. So this low pass filter which is acting as an integrator. So see the circuit diagram of low pass filter. This is the circuit diagram of low pass filter, which is consisting of input which is given to the low pass filter circuit, and it will get the output. So for the low pass filter we have the different types of input signals, that is impulse, step, ramp and square wave, triangle signals. So these are all the different input signals which are given to the low pass filter, and the low pass filter which gives the frequency responses of the signal. Frequency response of the signals. Let us see the circuit diagram. Here for the low pass filter we are applying the integrals, so that can be represented as V naught of t proportional to integral Vn of t. That can be, this is the equivalent circuit diagram of low pass filter. Equivalent circuit diagram of low pass filter. Equivalent circuit diagram of low pass filter. V naught of t is equal to 1 by c integral I of t dt. Here I of t is the, according to the Ohm's law, I is equal to V by R. So V naught of t is equal to 1 by c integral VR of t by R dt. Here we have the different timing responses, that is if RC for less than t, RC for greater than t, RC is equal to phi 2. If we are applying the time constants, that is RC for greater than t, the signal which is present at the circuit itself. Okay, when you are applying the time constants RC for greater than c, the signal which is present in the circuit itself. So at that condition the capacitor will charges and it gives the final value. Let us see where the capacitor reach the final value. The condition is RC for greater than t. RC for greater than t, the capacitor, the input signal which is present in the circuits itself. When you are applying the time constant, that is RC phi tau, RC is equal to phi tau, then the signal, the capacitor will charges and it reaches to the final value, that is phi RC is equal to phi tau. VR of t is equal to Vn of t, that is I of t is equal to V by R. If Vc of t is very small, the capacitor will not stay. That means capacitor voltage is very small. If the capacitor voltage is very small, capacitor will not charge. So it remains in the same condition. At that condition, that is RC for greater than t, V naught of t is equal to 1 by c integral I of t dt. V naught of t is equal to 1 by c integral I of t dt. V naught of t is equal to 1 by c integral I means V by R, V by R t. So V naught of t is equal to 1 by RC integral V of t dt. So what are the applications of integrator? So here integrator which can be used in the stabilizing purpose. it is easier to stabilize an integrator than differentiator. Okay, integrator, which is it is easier to stabilize an integrator than differentiator, and it can also increases the gain, and it can be used in the frequency responses, and it is used in the sensitive noises, and it can be used in the limitation of bandwidth, and it can be used in the amplitude differentiators. It can also used in the amplitude differentiators, and it is more convenient to introduce initial condition as integrator. It is more convenient to introduce initial condition as integrator. So these are the applications of integrator. What is meant by integrator? Integrator, which can be used as a low pass filter. For the low pass filter, we are applying the integrals to the equivalent circuit. So by applying the integrals, and we are verifying the based on three conditions, that is RC for greater than T, RC is equal to 5T. So based on these conditions, the integrator can be V naught of T is equal to 1 by RC integral 0 to T V naught of T dt. This is the integrated circuit diagram. Next one, high pass filter. So for the high pass filter, we can also let us know the what is high pass filter. What is high pass filter? High pass means which allows only high frequency signals, and it attenuates the low frequency signals, which allows only high frequency signals, and it attenuates low frequency signal. See the circuit diagram. This is the circuit diagram. This is the graphical representation of high pass filter. Means for the low pass, it attenuates the low frequencies now. So low frequencies, at the low frequency gain is decreases. At higher frequency the gain is constant, that means increases. This is the graphical representation. So it allows only higher frequencies, and it attenuates the lower frequencies. High pass filter means it allows only higher frequencies, and it attenuates the lower frequencies. So for the high pass filter also, you have to apply the different types of input signals. What are the input signals here? Sinusoidal signal, step signal, pulse signal, square wave, exponential. So these are all the input signals. These are all the input signals which are applied to the high pass filter. By applying the different types of input signals to the filter, we have to observe the frequency responses. We have to observe the frequency responses. Now first of all, we are applying the sinusoidal input to the high pass filter. Sinusoidal input signal which is applied to the low pass high pass filter circuit. So high pass filter circuit diagram, which is inverse to the inverse components of the low pass filter. In the resistor place we have to place the capacitor, in the capacitor place we have to place the resistor. Okay, that is the difference, just inversion of components. So that is the high pass filter. We are applying the one input signal to the capacitor, that capacitor which is connected to the resistor. Across the resistor we are note down the output value. Let us see the input signal. The input signal, sinusoidal signal, which is applied as input to the capacitor. So at what condition capacitor will be charges? At what condition capacitor will be charges? At low frequencies. We are starting from the very low frequencies. If you are applying the very low frequencies, the capacitor will not change. It can be remains in constant condition. It remains in the constant condition. At very low frequencies, the capacitor cannot charge. It remains in the same condition, that is in constant condition. If you are increasing the input signal, input frequency, the capacitor will charges. The capacitor will charges. The capacitor will charges when it is reaching the certain value, that is lower cutoff frequency. That is when it is reaching the lower cutoff frequency, it occurs the lower cutoff frequency. That means this is the lower cutoff frequency. This is the lower. That means we are increasing the input frequency. At reaching some frequency, it breaks the curve and it will get the constant value. That means here it occurs the lower cutoff frequency. That value is known as the 70%. That is 0.707. 0.707. So, and again we are applying the input signal at a high frequencies. The capacitor charges at a high frequencies. Capacitor charges and produce the constant gain. That means constant output value at a high frequency. The frequencies, it allows the input signal and produce the bandwidth at high frequencies. The capacitor will charges and then it produce the signal and without any attenuation. Operation of low pass filter. For the low pass filter we are applying the operation of high pass filter when input signal is applied. So sinusoidal signal we are giving as a input signal for the high pass filter circuit. For the high pass filter circuit, we are increasing the input signal at very low frequency. Capacitor will not change; it can stay in same condition. And again, we are increasing from very low frequency to lower frequencies. At that condition, when it is reaching some certain value, that is lower cutoff frequency, that value is 0.707. When frequency is increasing, it occurs some lower cutoff frequency. That is known as 0.707. Again we are increasing the frequency, that means higher frequency. When it is reaching the input signal higher frequency, the capacitor will charges and then it produce the output signal once we are increasing the frequency at a high frequency, the value will be constant. So that is, let us see the expression for lower cutoff frequency. The bandwidth of the high pass filter is f2 minus f1. f2 is the higher cutoff frequency, f1 is the lower cutoff frequency, that is equal to infinity. Here f1 is equal to 0. Why we are taking f1 is equal to 0 means lower cutoff frequency is 0. Because of at lower frequency the signal the capacitor cannot change. That means it cannot change, it remains in constant conditions. No, so that's why we are taking as a 0.70. f1 is equal to 0, f2 is equal to infinity. That very high frequency the capacitor charges and then produce the infinite values. That's why it is taken as a f2 is equal to infinity. Let us see the expression for lower cutoff frequency. So we have to find out the magnitude of the signal and angle. So high pass filter circuit is, this is the high pass filter circuit. So for this high pass filter we are applying input. So let us applying the Laplace transfer to the circuit. That is equal to gain A is equal to V naught of S by VI of S. V naught of S by VI of S. That is equal V naught of S is V naught of S. That means here output, no? So R by input is to the combination of both resistor and capacitor. So V naught of S by VA of S is equal to R by 1 plus R by R plus 1 by CS. So if you take the RCS common, R common, so that is 1 by 1 plus 1 by RCS. So by putting S is equal to J omega, that is A is equal to 1 by 1 plus 1 by 1 C J omega. That A is equal to 1 by 1 minus J 1 by omega RC. That is omega is equal to 2 pi F. Omega is equal to 2 pi F. So magnitude of A is equal to 1 by square root of 1 plus 1 by 2 pi F RC whole square. Magnitude of A is equal to 1 by square root of 1 plus 1 by 2 pi F RC whole square. Gain is equal to V naught of S by VA of S. So V naught of S is R by R plus. See the circuit diagram of high pass filter, so you can understand. R by R plus 1 by CS. Putting S is equal to J omega, then A is equal to 1 by 1 plus 1 by RC J omega. A is equal to 1 by 1 minus J omega, 1 by omega, as omega means 2 pi F RC. So that is magnitude of A is equal to 1 by square root of 1 plus 1 by 2 pi F RC whole square. The theta is equal to tan inverse 1 by 2 pi F angle. So it will not get the frequency. Theta is equal to tan inverse 1 by 2 pi RC. So at the lower cutoff frequency F1 and the magnitude of response of the magnitude A is equal to 1 by square root to substitute in the equation 1. So equation 1 is magnitude of A is equal to 1 by square root of 1 plus 1 by 2 pi F RC whole square. This is the equation. We have to submit the magnitude of A to 1 by square root 2 into equation 1. That is, for the above equation we have to squaring on both sides and equating the denominators. 1 by 2 pi F1 RC is equal to 1. F1 is equal to 1 by 2 pi RC. The expression is the lower cutoff frequency for the high pass filter. Expression the lower cutoff frequency for the high pass filter. That is F1 is equal to 1 by 2 pi RC. Relation between F1 and tilt. Relation between F1 and tilt. Next topic is relation between F1 and tilt. The lower cutoff frequency of high pass circuit is F1 is equal to 1 by 2 pi RC. This lower cutoff frequency produces a tilt. That means at lower frequency, so signal is like this. This is lower cutoff frequency. Here we are producing the tilt. That means getting the break. That break is known as the tilt. So at lower frequency producing the some tilt. Producing the tilt. This is the tilt. When the capacitor is charges from initial value to final value. Initial value is the 10% and final value is the 90%. So for a 10% change in capacitor voltage, the time or pulse width T is equal to 0.1 RC is equal to PW. 0.1 RC is equal to PW and pulse width. 0.1 RC is equal to pulse width. Pulse width by RC is equal to 0.1. The fractional tilt. Fractional tilt is equal to pulse width by RC, that is 2 pi F1 PW. That F1 is equal to 1 by 2 pi RC. 2 pi F1 RC is equal to 1. Let us see the relation between F1. F1 is the lower cutoff frequency. Tilt. At tilt it produces the at lower frequencies, that is when the capacitor is changes to 100%, so that pulse width is T is equal to 0.1 RC, that is equal to PW. Pulse width by RC is equal to 0.1 is the fractional tilt. So fractional tilt is equal to PW by RC is equal to 2 pi F1 pulse width. So from that equation we have to calculate the lower cutoff frequency, that is F1 is equal to 1 by 2 pi RC, that is equal to 1. So let us calculate the RC time constants. RC is equal to 1 by 2 pi F1. Pulse width by 1 by 2 pi F1 is equal to 1 by 2 pi F1 PW. So this equation which applies the when the capacitor is charges to the 10%, at 10% it occurs the some tilt. From when the tilt exceeds 10%, the voltage should be treated as exponential. That means the signal is getting anything. So after occurring some tilt, then signal will produce the signal voltage will produce the exponential signal. So that is equal to V naught of T, V out is equal to Vf means final voltage minus Vf minus Vi e power minus T by Rc. That means the signal which is increasing from initial value to, that means 10% to 90%. Signal is exponential signal. That means final value V out is equal to Vf minus Vf minus Vi e power minus T by Rc. The signal which is varying exponentially with the time constants from 90%. That is the relation between F1 and tilt. That is the relation between F1 and tilt. Next topic is high pass filter circuit for step input. So now we are applying the step signal to the high pass filter. Before we applied the sinusoidal input to the high pass filter, then we observe the what is the response of the lower cutoff frequency. Now we have to observe the frequency response of step signal when it is applied to the high pass filter. So here we have the three conditions, that is RC less than 0, RC greater than 0, RC greater than 5 tau. RC greater than 5 tau. The step signal which is operates based on three conditions, that is RC less than 0, RC greater than 0, RC greater than 5 tau. RC greater than 5 tau. Let us see the first case, that is RC less than 0. When step signal is applied to the high pass filter, this is the step signal. This is the step signal when it is given to the high pass filter circuit. High pass filter circuit. This is the high pass filter circuit. So this is the response of the high pass filter when step signal is applied to the high pass filter in three conditions, that is T less than 0, T greater than 0, T greater than 5 tau. So these are the three conditions. We have to observe the frequency response of the step signal. When step signal is applied, that means when the step voltage is applied, the capacitor is cannot change. That means we are observing at the T less than 0. At T less than 0 condition, when the step signal is applied, the capacitor cannot change. That means capacitor cannot charge, so that it cannot produce any output values, so that the output is 0. V out is equal to 0. V out is equal to 0. T less than 0, the step signal is applied, but capacitor cannot change. It remains in constant condition, so that it does not produce any output value. That is, V is equal to 0, V out is equal to 0. At the t less than 0 condition. Now we are applying the t greater than 0. At t greater than 0, the capacitor is charges and then it produces the output exponentially towards its steady state condition. That means we are applying the some high voltage step signal to the high pass filter signal circuit. So capacitor is charges and then it produces the output with the exponential signal like this. So some exponential signal like this, some exponentially signal. So at that condition we have to observe the input Vf is equal to 0. That is forward voltage is equal to 0, Vin is equal to V. We are applying with the input signal as a V voltage. At that condition Vf is 0. By putting these values into the final expression, that is a high pass filter output signal, that is Vout is equal to Vf minus Vf minus Va e power minus t by Rc. That Vf is equal to V e power minus t by Rc. At greater than t less than 5, at greater than 5 tau, the output will reach the 99% of its final value. At t less than 0, the capacitor cannot change, so the output is 0. At t greater than 0, capacitor charges to initial value, that is 10%. Then it produces the exponential signal, that is Vout is equal to V e power minus t by Rc. Now we are changing the condition, that is t greater than 5 tau, the capacitor is charges and it reaches its final value, that is 99%, so that it produces the output value, that is so in this condition the capacitor is charges automatically. In this condition the capacitor is charges automatically and changes its condition. In this condition we produce the infinite current. At t greater than 5 tau condition, it produces the infinite value, infinite current. The capacitor changes instantly. So the voltage across the capacitor can be written as V0 of t is equal to 1 integral 0 to t I of t dt is equal to 0. In this condition, when t greater than 5 tau, the capacitor is charges and it changes its conditions and then it produces the infinite currents and it produces some voltage across the, then the voltage is given as V0 of t is equal to integral 0 to t I of t dt, that is equal to 0. So the step signal works based upon the three conditions, that is t less than 0, t greater than 0, t greater than 5 tau. At t less than 0, the capacitor cannot change, so it does not produce any output values. At t greater than 0, the capacitor changes instantaneously and then produce the output voltage exponential signal, that is V e power minus t by Rc. At t greater than 5 tau, the capacitor charges and changes its conditions instantaneously and then it will produce the output voltage across the capacitor. Then it is at that condition it produces the infinite current. So infinite current across the capacitor. At V0 of t is equal to integral 0 to t I of t dt is equal to 0. This is the response of the step signal. The final responses. This is t less than 0 condition, that is t greater than 0. This is t greater than 5 tau. So this is the three responses: t less than 0, t greater than 0, t greater than 5 tau. So this is the step response of the different time constant. Time constants are t less than 0 or RC less than 0, RC greater than 0, RC greater than 5R, 5 tau. So that is the three responses of the high pass filter when the step signal is applied. So in next section we will know about the step signal when it is applied square wave signal when it is applied to the high pass filter. We completed the sinusoidal signal and step signal. In this section we can know the remaining concepts of the high pass filter, different types of input signals of the high pass filter. Thank you one and all. If you have any doubts you can ask me, and regarding video you can also ask any doubts.